Hi there, this is Further Mechanics, Circular Motion Lesson 4, part of the A-Level Physics. Let's move on then. Let's do this one first. So, recap question from last lesson. So, you want to pause and have a go. A helicopter circles continuously at a constant speed around a horizontal path of diameter 850 meters, taking 4 minutes to complete each job at the path. What are the speed v and the centripetal acceleration a of the helicopter? So, speed, v equals 2 pi r over t. So we've done this previously. So that'd be 2 pi times the radius. Now you've got to be careful because we're given the diameter, not the radius. So we need to times by 425 meters. Divided by the time period. So 4 minutes is 240 seconds. Which gives a velocity of 11.1 meters per second. Let's do the acceleration. So acceleration, v squared over r. So it's just the 11.1 squared. Use the full number in your calculator if you can. Divided by the radius, 425 meters. That gives an acceleration of 0.29 meters per second squared. So let's move on. Let's look at centripetal force. So this is basically a Newton's law application of the equations from last lesson, the A equals V squared over R, A equals R omega squared, and A equals V omega. So we just need to basically substitute in the F equals ma. So if a body is accelerating, it must be subject to a resultant force. The direction of the resultant force and the acceleration must be the same. Therefore, centripetal acceleration requires a resultant force directed towards the centre of the circular path, and we call it centripetal force, which makes sense because we call the acceleration centripetal acceleration. So tension provides the centripetal force required by the hammer thrower. So what happens when centripetal force is removed? This question gets asked quite a lot. So this object's in orbit, and if the centripetal force is removed, it'll just move off at a tangent to the path. Let's move on. Some other examples of centripetal forces. So if you want to pause and have a think, have a go at this. Earth orbiting the sun, what do you think that is? Centripetal force is the gravitational force. What about a car going around a bend? That's the friction on the car's tyres. Airplane banking, so when an airplane turns, that's the push of the air on the airplane's wings. In the last situation, what about an electron orbiting a nucleus? What do you think provides the centripetal force? That would be the electrostatic force. Let's keep going. So, equations for centripetal force. We know that Newton's second law is the sum of the forces is mass times acceleration. And then we can just substitute in the equations from last lesson, the A equals V squared over R, and A equals R omega squared, and A equals V omega. So that gives us these three equations, if you want to write these down, because we're going to use them. The sum of the forces notation will become very apparent in a couple of questions' time. So we've got force equals mv squared over r, mr omega squared, and mv omega. Just like the centripetal acceleration, the bottom one is not used as often as the others. Just so you're aware of that. But sometimes you may need to use it. So let's have a go at this one. If you want to pause, have a go. Calculate the centripetal tension force in a string used to whirl a mass of 300 grams around a horizontal circle. When it's a horizontal circle, this will become more apparent when we do vertical circles. We just need to use the equation on its own. We don't need to do anything else, and you'll see why. It'll be clear, by the end of this session. So let's get the force. So force is equal to mv squared over r. Let's just put our numbers in. So the mass is 300 grams, which is 0.3 kilos. Times the speed. Well, the speed is 3, so let's square that to get 9. And then divide by the radius of 80 centimeters, which is 0.8 meters. That gives a force of 3.4 newtons. That should be pretty straightforward. Let's get rid of that and move on. If you want to have a go at this one, just pause. So calculate the maximum speed that a car of mass 1500 kilograms can go around a curve of radius 40 meters if the maximum frictional force available is 10 kilonewtons. So mv squared over r. And let's rearrange to get v. So that'd be fr divided by m square root gives v. Then we just need to put our numbers in. So we got the force of 10 kilonewtons, so 10,000 times the radius, which is 40 meters, so times 40, divided by the mass, 1500 kilograms. Then we just need to square root that, and that gives us a velocity of 16.3 meters per second. Hopefully that's okay. Let's move on to the next bit. So these are the ones that are likely to come up in examination questions. So we've got a mass of 200 grams. Well, if you want to pause and have a go, that'd be great. We've got a mass of 200 grams, which is whirled around in a vertical circle using a piece of string of length 20 centimeters at 4 revolutions per second. We're going to calculate the tension in the string at positions A at the top, B at the bottom, and C horizontal. So the first thing that we need to do, and this will make sense shortly, is to find the velocity. So there's an equation. The one that you're used to is the v equals 2 pi over t, but we're going to use v equals 2 pi rf. So that would be 2 pi times the radius, which is 20 centimeters, so 0.2 meters, times the frequency. Now the frequency is 4 revolutions per second. 4 revolutions per second is a frequency of 4 hertz. So we've got 2 pi times 0.2 times 4. So that gives us a velocity of 8/5 pi. I'm going to use this just for the accuracy, so just the full number. You can use a decimal if you want and just save it in the calculator. So we're going to use that velocity, you need to write this down, to answer the questions. So we'll do the top first. So I've drawn the forces on already. So we've got the tension acting down and the weight acting down, and the centripetal force always acts towards the centre. So the centripetal force goes down as well, mv squared over r. And then what we need to do is apply the equation. So the equation is the sum of the forces is equal to mv squared over r. So the sum of the forces is, we've got the tension and the weight. So the tension and the weight act in the same direction, and we're going to take down as positive because everything's going down. So the sum of the forces is the tension plus the weight equals the centripetal force mv squared over r. Then what you need to do is just to rearrange to find t. So if you want to have a go, if you got this wrong and want to have a go at that from there, please do. So tension is equal to mv squared over r minus mg. And I'm going to factorize and pull the m out straight away, just for the sake of room. So that'll be v squared over r minus g. Then we just need to put our numbers in. So the tension is equal to the mass, which is 0.2 kilos. V squared is the 8/5 pi, but make sure that you square all of that, divided by the radius, which is 0.2 meters, and then minus g 9.81. Put that in your calculator, and you should get a tension of 23.3 newtons. Hopefully that's okay. So let's have a go at the other one at the bottom. It's the same process. It's just that the forces initially are acting in different directions. Well, one of them is. So let's have a look. So this is at the bottom. As you can see, the tension's acting upwards. The weight is now acting down, as weight always acts down. And acting upwards, we've also got mv squared over r, because the centripetal force always acts towards the centre of rotation. So same again, we just need to apply the law. So the sum of the forces is equal to mv squared over r. So let's sum the forces. We're going to take up as positive because the centripetal force is going up. So we've got tension going up minus the weight mg equals mv squared over r. So just like last time, but this time it's t minus mg rather than t plus. Then we just need to rearrange to get t. So I'm going to factorise at the same time. So tension is equal to mv squared over r plus mg. So m is going to be v squared over r plus g. So it's exactly the same as last time, but this time we're adding g rather than taking away. Let's put the numbers in. So the mass is 0.2. Brackets. The v squared is 8/5 pi squared. 8/5 pi squared. Make sure that's all squared. Divided by the radius, 20 centimeters, so 0.2 meters. Plus this time 9.81. So the only difference between the top and the bottom is adding 9.81 rather than taking it away. So that gives a tension of 27.2 newtons. Again, I hope that's okay. Let's move to part C. Remember to pause at any time or rewind if you need to. Part C, horizontal. So, special case. When it's horizontal, the weight is acting perpendicular to the direction of the centre of the circle. Therefore, it has no effect on the centripetal force. So we can simply do F equals mv squared over r. So when it's in the centre of rotation, when it's horizontal in a vertical rotation, it just acts like it's a horizontal rotation. From earlier when we did the question where it was whirled in a horizontal circle. We just need to use mv squared over r, so let's do that. So we've got 0.2 times v squared, so the 8/5 pi. Make sure all that's squared. Divided by the radius, which is 20 centimeters, so 0.2. Put that in your calculator, and you'll get a force of 25.3 newtons. And then what I've got is another example question. It's the same principle, so you can do some practice if you struggled with this. Let's move on. So here we go. Let's pause, do this. A bob of mass 0.6 kilograms is suspended from the end of a piece of string 0.5 meters long. The bob is rotated in a vertical circle. So as soon as you see vertical circle, you've got to understand that it's the sum of the forces. Remember, it's horizontal circles, to just use F equals mv squared over r. At a constant rate of 120 revolutions per minute, calculate the tension at the top and the bottom of the rotation. So we're going to do the top first. So the top of the rotation, we've got the weight acting down, mg. We've also got the tension acting down and the centripetal force acting down as well. So we need v first. Let's get v. So v is equal to 2 pi rf, so 2 pi times the radius, so times 0.5. Times, now we need frequency. So we've got 120 revolutions per minute, which will be 2 revolutions per second. And 2 revolutions per second is the frequency of 2 hertz, so times 2. So that gives a velocity of 2 pi meters per second. So let's apply the law. So sum of the forces is mv squared over r. So everything's going in the same direction, so it's t plus mg equals mv squared over r. Then I'm going to rearrange to find t and factorise at the same time. So the tension is equal to, so pull the m out, so it's v squared over r minus g. Then let's put our numbers in. So the tension, so we've got mass as 0.6. We've got v squared. So that'll be 2 pi squared. So that's simply 4 pi squared divided by the radius, which is 0.5, minus 9.81. Calculate that. That gives a tension of 41.5 newtons. Hopefully after doing the example, that's okay. So I'm going to clear this and then we'll do the bottom of the rotation. Remember to keep note of the velocity of 2 pi meters per second. So at the bottom, little diagram. So we've got the bob there. The tension this time is going up and the weight is in the opposite direction acting down, and the centripetal force is always acting towards the centre. So this time we need to apply the sum of the forces is mv squared over r. So the sum of the forces now, taking up as positive, is T minus mg this term, equals mv squared over r. So then to get tension, we need to take the mg over, and I'm going to factorise, take the m out, so it'd be v squared over r plus g. Then we just need to put the numbers in. So we've got 0.6 multiplied by, so v squared, so that's 4 pi squared, divided by the radius, so 0.5. And this time we're going to add the 9.81. And that will give you a tension of 53.3 newtons. So that's the end of circular motion. Hopefully that's okay. Those examples have helped. And I'll speak to you soon. Thanks for watching.